Okay, so in this case, we're going to find the homogeneous transformation matrix for a rotation of 90 degrees about the axis. And we also, meanwhile, this object is going to have a displacement of 3 units in the y0 direction. So before we can synthesize the transformation matrix H, we will need to know R, the rotational matrix, and the vector, which is D, and put 1 over here and put 3 zeros over here. So let's start. So we know the rotation is going to be about the axis, and it's going to be 90 degree. So this is a formula that we're going to use. And this formula can actually be obtained in the previous part of your notes, which is cosine phi, negative sine phi, sine phi, cosine phi, 0, 0, 1, 0, 0, which should be pretty straightforward. Cosine phi, cosine 90 degrees is going to be 0. This is going to be negative 1. This is going to be 1. This is going to be 0. We got 2 zeros over here and 2 zeros over here. And this component over here is going to be 1. So we get the rotational matrix by using the formula we identified earlier. The other thing we need to know is the matrix, the vector. We say that it's going to be move along y0 direction with 3 units. And we are now moving along x direction, so it's going to be 0 over here. But we do have 3 over here, and we get another 1 over here. So we got these two important information we need to have. So go to next page. We have defined the matrix based on what we learned in the previous page, and we know it's going to be 0, 3, and 0 over here. So put everything all together. This is my R, this is my D, those are my 3 zeros, and I got 1 over here. So this is going to be something we are trying to have. And if we can measure the position in the first frame, which is 1, 0, 0, and we try to find the position measured in zeroth frame. So that should be pretty straightforward. P0 is going to be H P1 0 to 1. So this is something we're going to use over here. So in this case, we are having we are having 0, 1, 0, negative 1, 0, 0, 0, 0, 1, 0, 3, 0, 0, 0, 0, 1. And the vector over here, keep in mind, this time, we are not having 1, 0, 0 only. This is 3 by 1. This is 3 by 3. This is 4 by 4. So when we try to do P not equals to H0, 1, and P1, this is going to be 4 by 4. In order to get another vector over here, this must be 4 by 1. So the question becomes, okay, now I know what's going on over here. What is the fourth component over here? In order not to change everything, we will put 1 over here to remain everything constant. And when we do the inverse, we can actually get everything back to its correct number. So this is my original P. And after the P, you will need to add another 1 as your fourth component. So if you do the calculation, you're going to find the answer is going to be 0, 4, 0, 1. This is a big P. This is also a big P. So you might find this one is also 4 by 1. So it means that the fourth component is not part of the three-dimensional position. You're right. So when we are saying the P naught, which is measured in the first frame, that should be just three components, 0, 4, and 0. This is going to be the answer. So if you have a transformation, you have rotation and linear translation in your system, then you synthesize a matrix which is 4 by 4. But we do need to have another additional components as a fourth component in our vector. We always use 1. So when you synthesize something like this over here, we multiply that by our transformation matrix. We should be able to get another vector that describing the three-dimensional position in the desired frame. But keep in mind, it's going to be three components. So the fourth component, you must have 1. So when you have that 1 in your answer, just get rid of that. Keep the first three components, and that is going to be the position in the three-dimensional space you desired. And that is going to be this part. So the next thing is, okay, now I know how to transform from one frame to the other one is great. But what if after a while, this part over here, I can measure that. I can measure the movement of the robot after 30 minutes. Now, I do need to know what is the position related to its original coordinate, how it's going to be look like. And if I do not have sensor or my sensor failed, back when the tool head has been rotated for 30 minutes. So how can I get the information from one end back to its original position? Now, this time we would need to use inverse transformation. The inverse transformation is actually pretty straightforward. We are using the similar system, but this time instead of using R, the H inverse transformation matrix is well defined. So this is a formula that we're going to use for this kind of a transformation. Keep in mind the transpose of the rotation matrix is going to be 3 by 3. And the 3 by 3 matrix multiplied by the vector is going to be 3 by 1. So you still need to fill 3 zeros in the fourth row over here and another 1 as a fourth component in the fourth row. So this one you synthesize is going to be a 4 by 4 matrix. Once you get this part down, you should be able to convert from one end to the other. So use the example we have earlier. Let's go back to the previous slide. We got our R, 0, -1, 0, 1, 0, 0, and 0, 0, 1 over here. So we would need to use the formula, which let me write it down over here. H inverse is going to be RT, -RT, D, 0, 1. And my RT is going to be the transpose of the R, which is going to give me 0, -1, 0, 1, 0, 0, 0, 0, 1. And the D is still 0, 3, 0 along Y naught direction. So there are a few things that we might want to calculate before we start. One is RT D negative in front of it, which is going to be negative. If you do the calculation over here, you're going to find this specific vector is going to give us -3, 0, 0. So fill in the blank of this specific matrix. We got our H -1, H inverse. Pretty straightforward, right? Because it's just RT. Then it's going to be this part as a vector, which we're going to have. Then we will need to have 3 zeros over here and one component over here. So the P1 is going to be H inverse P naught. This time, just be careful because when we say the P naught, this one is going to be 4 by 1 since this is 4 by 4. So when we are doing something like this, I'll copy down everything we have over here and put it into this matrix over here. Okay, so we know there are 4 components over here. Based on what we have in the previous slide, it should be 0, 4, 0 in 3 dimensions. But what we get as a big P0 is actually 0, 4, 0, 1. This is the one that we're going to use in this calculation over here. So it's going to be 0, 4, 0, 1. If you forget, it's actually okay because we only need to use the first 3 components and the fourth component is always 1. So if you keep that in mind, it shouldn't be too difficult for you to identify what the vector is going to look like. Then if you do the calculation over here, you're going to find the answer is 1001, which means my P, small p, 1 is going to be 1, 0, 0 over here. So you can check this answer with the original problem statement. Few slides back, this one over here. So we try to identify the position after transformation, and the original position is going to be 1, 0, 0, which is identical to what our calculated result over here. So if you know how to do the transformation and you transfer from one coordinate to another coordinate, then you use the inverse method to transform from the designated coordinate into its original coordinate. You should get the same answer. If you fail to get those same answers, your calculation has something wrong. That finish up the concept of this module. We're going to have some assignment in the end of module. Please turn in that in time. That's what we have for this module.